Hello students! If I'm not mistaken, this lesson today is going to be our last lesson where we learn new techniques of differentiation, and then after that we move on to various kinds of applications of derivatives. So, I believe this lesson is probably going to be rather long. In fact, chances are I'll split it into two different videos, but if I rush it, then it's just not going to make a whole lot of sense. So I feel like it's important today to take the time we need to go over these concepts without rushing too much. Now, the concepts that we're learning today, some of them at least, relate to logarithms, and we know when we think of logarithms, we need to think of their inverses, which are exponential functions or exponential expressions. So we're going to start by differentiating each of these exponential expressions. And notice it says differentiate with respect to x. So x is our variable. So we know the derivative of e to the x with respect to x is just e to the x. And previously we learned, even though maybe we've forgotten because we don't use it very much, but the derivative of 2 to the x with respect to x is 2 to the x times the natural log of 2. And the derivative of 3 to the x is 3 to the x times the natural log of 3, etc. for any base. 4 to the x, it would be 4 to the x natural log of 4, and so on. Okay, so now let's do a little bit of implicit differentiation. So the derivative of e to the y with respect to x would be e to the y times y prime. The derivative of 2 to the y with respect to x would be 2 to the y times natural log of 2 times y prime. The derivative of the inside is y prime, and so on. The derivative of 3 to the y times natural log of 3 times y prime. Okay, so now moving on to our lesson. This is notes number 29. We're going to do two different kinds of derivative techniques, those for logarithms and those for inverse trig functions. So just a really brief review of logarithmic functions. You have logarithmic growth, which has that kind of shape if you graph it. And that would be if the base is greater than 1. So natural log is an example because the base is e, and e is about 2.7, or log base 10, or log base 2, etc. Base is greater than 1. And then logarithmic decay looks like this. That would be if the base is between 0 and 1. So an example would be log base 1/2 of x. And for either of these, you have a vertical asymptote, the line x equals 0. So the domain is x is greater than 0. Okay, so that means whatever is in here has to be greater than 0. Even if it's something more complicated, like even if you have log base 2 of x squared plus 7, well, x squared plus 7 has to be greater than 0. Okay, so how about the derivative of the logarithmic function y equals natural log of x? Here's what we're going to do. We're going to rearrange the equation into something that we can differentiate. So we know that y equals natural log of x can also be written like this, y equals log base e of x. And based on what we know about logarithms, this means the same thing as e to the y power equals x. So here we have an implicit equation, and we can differentiate it implicitly, and we would get e to the y times y prime equals 1. We take the derivative of both sides. Now let's isolate y prime. Y prime is 1 over e to the y. And earlier we said that e to the y was x, so I'm going to put x in there. And that gives me y prime equals 1 over x. So what does that mean? That means that the derivative of the natural log of x with respect to x is 1 over x. Okay, so that's a new derivative rule for you to learn. Make sure that's really standing out in your notes. Now, natural log is not the only kind of log, so we need to generalize this. What if we had y equals log base a of x? Remember, the base a still has to be a number that's greater than 0 and not equal to 1. So let's rearrange this equation just like we rearranged the previous equation and take the derivative of both sides using implicit differentiation. We get the derivative of a to the y is a to the y times natural log a times y prime, and then the derivative of x is 1. Isolate the y prime, divide by a to the y and divide by natural log of a, and then replace a to the y with x right here. And that gives us y prime equals 1 over a to the y. Oops, I was replacing that, wasn't I? 1 over x natural log a. So that means that the derivative of log base a of x with respect to x is 1 over x natural log a. Now theoretically, you only need this one rule, because if you're doing natural log, that means log base e, you could still use this rule and you would have 1 over x times the natural log of e, and the natural log of e is 1. So it's still 1 over x. Okay, so now what we want to do is incorporate this rule with our other rules, but I just decided to throw in a real simple one for problem number 0. So problem number 0 is to find y prime if y equals log base 3 of x. So we're just using the rule that we just came up with. Memorize the rule, apply it. You get y prime equals 1 over x natural log 3. Okay, number 1. Now we're using the chain rule. So to use the chain rule in conjunction with the derivative of a logarithm rule, instead of 1 over x for the derivative of natural log, it's 1 over whatever is in there. So 1 over sine of x instead of 1 over x times the derivative of the inside. We have to use the chain rule. So the 1 over sine x was the derivative of the outside, the derivative of the natural log function, and then times the derivative of the inside. Derivative of the inside is cosine x. This one is pretty easy to simplify because we know that cosine x over sine x is cotangent x. Number 2. Same idea. It's very similar to number 2, but instead of natural log, it's log base 10. So again, we're going to use the chain rule and the derivative of the outside. So the derivative of a log base 10 function is 1 over its inside natural log 10. Then multiply by the derivative of the inside. So there's where we get our cosine x, and then we can simplify that. Again, cosine x over sine x is cotangent x, so we would have cotangent x over natural log 10. Number 3 is kind of like number 1 because we have a natural log function and something else inside it, and so we're going to use the chain rule. But notice that the inside here actually has an inside of its own. So inside the natural log, we have our square root, and inside the square root, we have x squared plus 1. So we have 3 layers of the chain rule here. So the derivative of natural log, 1 over the inside, times the derivative of square root, so think of that as the 1/2 power, so 1/2 times the quantity raised to the negative 1/2, times the derivative of the inside is the derivative of x squared plus 1, and that's 2. So this one actually simplifies really nicely because you can take your 1/2 times 2 and multiply them together, and that's just 1. So you can think of that as those canceling. And then you can take your x squared plus 1 to the negative 1/2 and think of it as 1 over, here let me write this first part, think of it as 1 over the square root of x squared plus 1. So when you multiply those square roots together, we just have 1 over x squared plus 1. And then number 4. So this one is like number 2 because we have some other kind of logarithm, which is not a natural log, and then it's also like number 3 because we have the inside function to deal with. So the difference between 3 and 4 is that we need not just 1 over the square root of x squared plus 1, but we need to multiply that by the natural log of 3. That's that extra piece that we have in the denominator, just like we saw in problem number 0. Then we're going to multiply by the derivative of the inside. So that's going to look like exactly how it looked in problem number 3. So we'll be able to do the same kind of simplifying and end up with 1 over natural log 3 times x squared plus 1. All right, let's see what's next. Okay, so a few more examples where we're combining the derivative of a logarithmic function with other rules. So in problem number 5, we're combining it with the product rule and needing to know the derivative of a trig function. So using the product rule, we have the first times the derivative of the second, and the derivative of natural log x is 1 over x, plus the second times the derivative of the first, which is cosine x. There's really not much we can do to simplify this. We could write it as sine of x over x, and you could decide if you want to put cosine x before natural log x or whatever. I'm not sure that it really matters. Number 6 is the same idea. We're using the product rule, but notice that I have a different kind of logarithm, not a natural log, and I also have 2x, not x. So this is combining a lot of things. So we're starting with the product rule, the first times the derivative of the second. Now when we take the derivative of log of 2x, we're going to have 1 over 2x natural log 10, remember because log is log base 10, times the derivative of the inside, so that would be times 2. So this whole thing here is the derivative of the second, plus the second times the derivative of the first. So the derivative of sine of 2x would be cosine of 2x times 2. So we're using the chain rule. Right here we used the chain rule, and right here we used the chain rule. So let's see, what can we do? So make sure you're aware that this 2x cannot cancel with this 2x, because this top 2x is inside the sine function, this bottom 2x is not inside the sine function. So those don't cancel. So what we can do is just write it as a fraction, sine of 2x over 2x natural log 10 plus, oh, guess what I didn't notice? There's a 2 there and a 2 there. We can cancel those. So let's get rid of that 2 that I wrote. And then nothing we can do over here, just rewrite it as 2 log of 2x cosine of 2x in whatever order you wish. Okay, next one, lucky number 7. Oh boy, quotient rule. Let's go. Y prime equals the bottom. Oops, got my plus sign. The bottom times the derivative of the top. The derivative of 1 is 0 minus the derivative of a log of x is 1 over x natural log 10 minus the top times the derivative of the bottom, 0 plus 1 over x natural log 10 over the bottom squared. Okay. So now let's see what we can do with this. I feel like distributing. We're going to ignore that I wrote 0 minus there. Still need the minus though, don't we? Okay, so let's distribute. And we have negative 1 over x natural log 10 minus log of x over x natural log 10 minus 1 over x natural log 10 plus log of x over x natural log 10 all over our denominator. Do we have any like terms? We do. We have 2 pairs of like terms, and actually these 2 cancel. And then these 2 can be added together to give us negative 2. So we have negative 2 over x natural log 10 over 1 plus log of x squared. And that can be written as -2 over x natural log 10 times 1 plus log of x quantity squared. All right. So that takes us through the first part of this lesson. And I'm going to save the second part for video number 2.